Thomas's father, Lou, was about the smartest person I ever met, not to disparage anybody, but certainly one of them. And Lou is just as, Thomas is just as smart, amazingly enough. He's gone from being director of the office in the State Department on weapons. It's WMD, weapons of mass destruction. He was controlling weapons of mass destruction and stopping them from falling into the hands of terrorists. He went on to Teamworthy. He's got hundreds of startups launched under his surveillance. And now he's citing Vannevar Bush with regard to accelerating the endless frontier. And Vannevar Bush always interested me because he was the chief voice for analog computing. He built the analog computer, as he called it, and he believed that it was going to prevail. And one of his students, I believe, Claude Shannon, demonstrated the superiority of digital. So Vannevar Bush has a reason to understand the importance of paradigms, and Thomas is going to introduce his paradigm, endless frontier.
All right. George, thanks for that extraordinary introduction, way beyond what I deserve, but certainly my father deserves it. He's been a tremendous teacher and guide in my life. Can you guys see the slides? Are we, maybe we're, okay, good. Slides are loaded up or no? No, they're, okay, here we go. All right, good. All right. Hardly a day goes by without another article on how, here we are, on how the U.S. is either falling behind China or will soon be overtaken by China in basic science, research, and technology. Some cite the rising level of R&D spending in China, while others note that China now has more PhD graduates in STEM fields than the U.S. does. These articles, of course, raise an important strategic question. How should the United States respond to the rise of China in science and technology? I would propose that the first step consists in asking the right questions. Probably the wrong question on this slide is the first one. Is the U.S. investing enough in R&D to maintain our scientific and technological advantage? It reminds me of the question often posed about our nation's spending on K-12 schools over the last 50 years. The right question regarding funding for our nation's schools was not how much we should spend on education, but how we should spend it, and specifically whether business model innovations like charter schools could enable better outcomes. The more important questions, I believe, are the others on this slide. What are the most important challenges facing emerging scientists, researchers, and investigators working in the U.S., and how can policy ease those challenges? In a coming era of likely federal budget constraints, what kind of new institutional arrangements or business models can help us maintain or extend the U.S. scientific and R&D competitive advantage? What does one of the most significant discoveries and inventions of the last 40 years, CRISPR and associated Cas9 gene editing, suggest about how we might improve the business models for basic science and R&D funding? And last, how can we redesign government R&D funding and business models to benefit from insights gained from other aspects of our nation's research and educational institutions? In short, the question is not only how much we spend, but how we spend it, and whether our method of funding is likely to reach those scientists and researchers, casting where the fish are swimming or planting seeds in hidden patches of fertile soil. Let's start off with some historical context of government funding of research in the U.S. to see whether it offers us any clues for the future. The earliest example of a federal agency for scientific research was the Survey of the Coast, established in 1807 during Jefferson's presidency, which eventually became the United States Coast and Geodetic Survey. The survey's primary responsibility was to map the coastline of the United States. This was followed by the establishment of the Depot of Charts and Instruments in 1830, whose primary mission was to take care of the Navy's charts, navigational equipment, and chronometers, and which eventually became the Naval Observatory, which is pictured that building on the upper right. Established during the Civil War in 1862, the Department of Agriculture, their primary mission, as articulated by its first commissioner, notably named Isaac Newton, was to conduct and disseminate agricultural research. The U.S. Geological Survey was established in 1879 with the responsibility for the, quote, classification of the public lands and examination of the geological structure of mineral resources and products of the national domain. However, many point to the Hatch Act of 1887. Now, this is different from the Hatch Act many of you are probably thinking about. There's actually more than one Hatch Act. My wife asked me if they were related to Orrin Hatch. I couldn't seem to find any connection. But as one of the earliest examples of federal funding for basic science and research, sponsored by Congressman William Henry Hatch of Missouri, the act provided each state with a block grant of $15,000 to set up agricultural experiment stations. The results of the experiments at these stations were to be published and made available for the benefit of farmers residing throughout the United States. In a similar way that patents laid open the inventions to the country, literally that's the root of the word patent, these stations laid open new farming techniques to the whole nation. The block grant structure of this funding gave states flexibility to determine how best to tailor these experiment stations to the needs of their communities and the opportunities for research they had identified. In the same year as the Hatch Act of 1887, Dr. Joseph Kinyoun, on the left, established the Hygienic Laboratory within the Marine Health Service on Staten Island, New York, a predecessor to the National Institutes of Health, and promptly focused on the fight against cholera, which was made incredibly urgent by the arrival of numerous immigrants flowing into Ellis Island and New York City. The seed of the NIH grew further with the passage of laws from 1902 to 1930. The first law passed in 1902 renamed the Marine Hospital Service as the Public Health and Marine Hospital Service. The service and Kinyoun's Hygienic Laboratory had already moved from New York to Washington, D.C. in 1891. The new law also set up the first formal research program in public health with the establishment of divisions of chemistry, pharmacology, and zoology. The new service was also authorized to hire PhDs for the first time, and not just MDs, which had formerly been the case. Congress passed the Biologics Control Act a few years later in 1906 to address some of the safety issues regarding the development of vaccines. Sound familiar? In 1930, Congress passed the Ransdell Act and redesignated the Hygienic Laboratory, which had been, again, at Staten Island originally, as the new National Institutes of Health. This act provided funding to construct 2 buildings and establish a system of research fellowships. But it's really in World War II that we see the relationship between science, R&D, and the U.S. government completely transformed. The requirements of the war, which brought us radar and the Manhattan Project, the scaling up of the production of penicillin, resulted in government involvement in nearly all aspects of basic science and R&D. As the war came to an end, FDR's director of the Office of Scientific Research and Development and former dean of the engineering department at MIT, Vannevar Bush, I think I'm pronouncing that correctly. Someone can correct me if it's Vannevar, but I believe it's Vannevar. He published a famous report called Science, the Endless Frontier, and outlined a vision for scientific research and development in a post-war environment. Incidentally, Bush also published a famous article in the Atlantic Monthly in the same year, 1945, called As We May Think, that foresaw machines that resemble the hyperlinking so common to all of us on the World Wide Web enabled by the internet. Bush's report, which synthesized the findings of a variety of committees, still offers us important insights regarding the role of government in supporting scientific research and development. His first insight was actually an historical one and even a philosophical one. He said that America is a frontier opening nation, echoing Frederick Jackson Turner's great book on the topic, Bush pointed to scientific research and advances as a still open frontier. Now that the Western frontier was settled and America had forsworn any further interest in colonies or overseas possessions, this endless frontier of science loomed large. His second great insight was that academic freedom and the pursuit of truth are foundational to science in the service of the general welfare. Bush wrote, quote, "As long as universities and colleges are vigorous and healthy and their scientists are free to pursue the truth, wherever it may lead, there will be a flow of new scientific knowledge to those who can apply it to practical problems in government, in industry, or elsewhere." His third insight was what works in war will not in peace, and is a variation on insight 2 regarding the importance of academic and scientific freedom. He wrote, quote, "We must remove the rigid controls which we have had to impose and recover the freedom of inquiry and that healthy competitive spirit so necessary to the expansion of the frontiers of scientific knowledge." His fourth insight, and perhaps his most important, was that scientific discoveries come from unexpected sources. Indeed, unexpected even to the investigator or the researcher. Scientific research is not a factory line, and it is not a linear process. He first cited medical discoveries to make this point, and he mentioned in the report Sir Alexander Fleming's serendipitous discovery of penicillin at St. Mary's Hospital in London, which when combined with scale-up partnerships with U.S. pharmaceutical companies saved countless American lives in World War II. Bush expanded his point about discoveries coming from unexpected sources by extending the argument beyond the medical sciences. He wrote, quote, "One of the peculiarities of basic science is the variety of paths which lead to productive advance. Many of the most important discoveries have come as a result of experiments undertaken with very different purposes in mind. The results of any one particular investigation cannot be predicted." Here he could have had in mind the work of Gregor Mendel, the Austrian Czech Augustinian friar and biologist, meteorologist, and mathematician, whose humble research in the garden of his monastery in Brno led to great insights in genetics and overturned some of the misconceptions of Darwin on heredity. Or perhaps he had in mind the development of insulin in Canada by a professor-graduate student team of Frederick Banting and Charles Best at the University of Toronto. Or maybe he was thinking of how radar developed from some initial research conducted by Watson Watts, a Brit, into the possibility of the Germans using radio signals to build a death ray, and then was tipped off by another scientist to explore the topic of the reflection of radio signals. As Bush saw it, basic research created a fund for new applications and products, something he understood well as the co-founder of Raytheon in the 1920s, the inventor, as George just said, of an analog computer called, I believe, the differential analyzer, and an advisor to the launch of the very first venture capital firm, American Research and Development Corp. He made the point that, quote, "New products and new processes do not appear full-grown. They are founded on new principles and new conceptions, which in turn are painstakingly developed by research in the purest realms of science." Bush also offered an important insight about the context that he was operating in. At the end of World War II, much wealth that had previously sustained medical research had been drawn down from both the effects of the Depression and World War II. He also mentions that, quote, "Industry is only to a limited extent a source of funds for basic medical research." His points do raise an interesting contrast with the current context we find ourselves in, where private foundations and enormous university endowments, as well as large companies, are more able to contribute to basic science and research, especially if tax policy and incentives are aligned to encourage such investments. Bush also recognized the need to strengthen medical research across the country, and not just in those regions and areas that have historically had the wealth to do so. He recognized the risk that his proposed National Research Foundation might become captured by the incumbent leaders in research, a problem common to government programs often referred to as agency capture. Quote, "The National Research Foundation must therefore be free to place its researcher grants not only with those institutions which have a demonstrated research capacity, but also with those other institutions whose latent talent or creative atmosphere afford promise of research success? Bush is proposing an architecture for seed funding of research at smaller institutions across the country. Bush noted also that science cannot ignore the question of employment and opportunity for the common man, including the forgotten man of the Depression. He made the case that science can even enhance competitiveness in international trade. He wrote, quote, "We will not get ahead in international trade unless we offer new and attractive and cheaper products. Where will these products come from? How will we find ways to make better products at lower cost? The answer is clear. There must be plenty of men and women trained in science and technology, for upon them depend both the creation of new knowledge and its application to practical purposes." The upper right is an advertisement for Raytheon and some of their products, again, the company of which he was a co-founder. His next insight pertained to the political economy of scientific research. He understood that tax laws shape the incentives to spend on research. He wrote, quote, "One of the most important factors affecting the amount of industrial research is the income tax law. The Internal Revenue Code should be amended to remove present uncertainties in regard to the deductibility of research and development expenditures as current charges against net income." Sound familiar to the discussions of today? Bush was gifted with and cultivated a subtle mind, attuned to the interplay of government and the private sector. Specifically, he cautioned that government support for R&D must encourage private support, not crowd it out. He stated, quote, "These private sources should continue to carry their share of the financial burden." However, other than his tax deductibility for R&D idea, he gave us no specific proposal for how that might be accomplished. We'll return to that theme later when we consider potential paths for reform. Likely foreseeing the competition with the Soviet Union, Bush also emphasized the importance of research to long-term military preparedness. He was especially keen to see the nation's research scientists focused on, quote, "far-sighted technical lines," end quote. You can almost imagine thinking of the possibilities of DARPA and NASA 10 years before they would become a reality, immediately after Sputnik in 1957. Bush grasped the inherent tension between the academic freedom and collaboration so necessary to technological advance and the wartime needs of keeping scientific research of military significance classified. However, he came down squarely on the side of the need for broad dissemination of basic science research during peacetime, while recognizing the need to protect sensitive military-related applications. His simple point was that a sounder foundation for a national security lies in a broad dissemination of scientific information upon which further advances can be readily made and our advantage against our adversaries sustained or extended. Bush also recognized the risks of abstracting science and research from the people actually doing the work, the scientists and the researchers. He noted in particular the contribution of President Conant of Harvard, who's pictured here on the right, to the work of the report when he wrote, "I cannot improve on President Conant's statement that, quote, in every section of the entire area where the word science may be properly applied, the limiting factor is a human one. We shall have rapid or slow advance in this direction or in that, depending on the number of really first-class men who are engaged in the work in question. So in the last analysis, the future of science in this country will be determined by our educational policy." Linking the success of our scientific research and development to our educational policy raises some interesting questions and possibilities for reform, which we will return to in a little bit. Bush concluded his report with 5 principles for a successful new agency that is devoted to basic science and research, which would later become the National Science Foundation, or NSF. First, this agency needs to provide stable long-term funding over a number of years to enable longer-term projects. Second, it must hire personnel who understand what Bush referred to as the peculiarities of scientific research and education. Third, such an agency, and this is one of the most important points, I think, should not run its own labs. It should make contracts and grants only. Bush sensed that an agency focused on or biased towards supporting its own labs would risk insular thinking and fail to identify the latent scientific talent across a wide range of institutions so necessary for scientific advances. Fourth, the agency must provide support to institutions but avoid seeking to control their decisions on policy, personnel, method, and scope. He concluded that the agency must maintain accountability to Congress and the President, which is necessary in a Democratic or Republican form of government. After Bush's report, beginning in 1945, the funding of science and research by the federal government continued to develop apace. Congress established the National Science Foundation, the agency that Bush had advocated for in 1950. The next major step, however, forward for basic science and research funding at the federal level occurred after the Soviet launch of Sputnik in 1957. As Americans and our leaders sought to avoid falling behind the Soviets in areas of critical technological and strategic importance, Congress, if you can believe it, in remarkable haste, or one might say responsiveness, established NASA and DARPA in 1958, just the year after Sputnik launched. The space age and the internet age would eventually follow. The atomic age and the Cuban Missile Crisis raised the stakes for preparedness for a nuclear attack. Some far-seeing scientists and researchers grew concerned that our communication systems were not sufficiently resilient or survivable in a nuclear attack. With the financial support of RAND, Paul Barron published On Distributed Communications in 1962, outlining a packet-based distributed communications network which offered the conceptual framework for the ARPANET, which would become the Internet and eventually the World Wide Web. The Internet would, of course, transform communications and reduce the transaction costs, something that Ronald Coase would appreciate, for scientists and researchers to collaborate not only in the U.S., but around the world. So as we come up to the 1980s and 90s, the federal budget for science and technology is growing ever larger. Policymakers and the National Academies of Science and Engineering are growing concerned that federal funds for science and technology are not being allocated properly. In issuing their report in 1995, these academies sought opportunities for improvement in the efficiency and efficacy of R&D funding and emphasized some of the same observations that Bush had highlighted 50 years earlier in Endless Frontier. Specifically, they noted the interplay of basic science and the development of innovative companies. Quote, Sun Microsystems and Silicon Graphics among computing companies, and Amgen and Genentech and biotechnology did not exist 15 years ago. All were started from a base of academic science supported by the federal government. Now, perhaps they're taking a little bit too much credit for the research done in the federal government, but they're making an important point about the interconnection between the two. This 1995 report also sought to address another concern that is just as relevant today, are the benefits of research spending flowing to foreigners instead of for the benefit of Americans and our general welfare and common defense. The report rebutted this concern by stating, history suggests instead that where research takes place has a direct effect on where it is put to use. The high technology firms clustered along Route 128 in Massachusetts, in Silicon Valley, in suburban Maryland, and Austin, Texas, all congregated around major federally supported university or government research centers. The report continued, if industrial use and centers of capital were the decisive factors, the foremost centers of biotechnology and computer firms should have located instead near Tokyo, Frankfurt, Paris, London, or New York City. However, one might question a little bit some of the conclusions. The relative decline of Route 128 as an IT corridor and the rise of Taiwan as the chip-making capital of the world certainly calls into some question whether some of these conclusions require revision. The same could also be said about the growth of China's R&D enterprise, which has sometimes come through research and industrial espionage, including the incidents and allegations involving Huawei. The 1995 report continued with a warning to complacent scientists and those that fund them. Over time, institutions and programs have been created that no longer serve us well. Even good programs and institutions must give way to successors that are better and are more closely linked to new national needs. Now, this process of replacement of the old by the new naturally happens in the business world through the processes of creative destruction outlined by Joseph Schumpeter in his 1911 book, The Theory of Economic Development. However, long-standing federally funded research projects have a way of staying in the budget. diverting funds away from planting the seeds for the next generation of important advances that often lack access to the channels of influence at the NIH or at the NSF. While it advocated for reforms in the allocation of science and research funding, the report also reminded readers of the same point made by Bush 50 years earlier, that major advances in science have often come from unexpected sources. The 1995 report cited some important contemporary examples of how the fundamental research on atomic clocks paved the way for the GPS system, how the work on the microwave spectrum of ammonia enabled the development of lasers, and how the studies of magnetic moments and nuclear spin spawned the rise of MRI technologies. However, by 2013, it had become increasingly clear that the gears of federally funded scientific research were gumming up with new regulations and process requirements generated by the federal funding agencies, as a report by the National Academies of Sciences, Engineering, and Medicine made clear. The report stated, though well-intended and undoubtedly appropriate, federal oversight and its accompanying burdens raise significant questions about whether the nation is optimizing its investment in our extraordinary research enterprise. The report continued in this vein of concern. Quote, the government-academic research partnership is under stress. Concerns have been raised repeatedly that federal laws, regulations, rules, policies, guidances, reporting requirements, while essential to a well-functioning, responsible system of research, have led over time to an environment where a significant percentage of an investigator's time is spent complying with regulations, taking time away from research, education, and scholarship. I recall George Gilder speaking earlier today on time, in this case, the investigator's precious time, as the essential economic scarcity. Echoing similar themes, a memorandum from the chairman of the National Science Board of the NSF in March 2014 stated, for more than a decade, surveys and reports have highlighted an increase in administrative and compliance requirements associated with federal research. There is now consensus that some of these requirements are interfering with the conduct of science out of proportion with the accepted need to ensure accountability, transparency, and safety. One can only imagine what new burdensome requirements may have arisen since that report 10 years ago, including some entirely unrelated to the pursuit of truth and excellence with integrity in the scientific enterprise. At the same time that the growing challenges facing researchers and scientists at our leading universities surfaced in these somewhat discouraging reports from 1995 to 2014, one of the great advances in basic biological science and medicine was underway. Let's turn to that story now to see what kind of lessons the discovery of CRISPR may hold for us as we consider how basic science R&D works today and opportunities for its improvement. Now, a show of hands from the audience. Who knows where Alicante is? So what part of Spain? Northern Spain? Southern? What's the nearest major city to Alicante? Valencia. Good answer. So I lived in Spain for nearly a year, and when I first heard about the University of Alicante, I had to consult a map. Was it near Sevilla, Barcelona, Madrid? Actually, no. As you said, it's on the east coast of Spain, not far from Valencia. There, Francisco Mojica, a professor working in the relatively young regional university, the University of Alicante, established only in 1979, was working on research related to archaea. Again, I hope I'm pronouncing that correctly. Single-celled organisms similar to bacteria. Mojica noticed a strange repetition in the DNA of these organisms, what he eventually renamed clustered, regularly interspaced, short palindromic repeats, or CRISPR for short. His work was initially rejected for publication by a number of journals, including Nature. But it would become the foundation of the most important advance in biology and biotechnology in the last 50 years. Still, it would take 2 decades until the significance of CRISPR would unfold in labs, conferences, and publications across the United States and Europe. It took a full decade. This is sort of a map of the development of CRISPR. It's actually a map put together by Professor Eric Lander, who's been somewhat critiqued for his role in the process of recounting the story of CRISPR, but I thought it was illustrative for the point. So just so as to preempt maybe some objections to the use of this map. But it took a full decade, as you can see from this map, for another scientist to recognize that CRISPR was an adaptive immune system, and another 3 years after that for experimental evidence to demonstrate that. Finally, in 2012, nearly 20 years after Mojica's discovery in Alicante, Jennifer Doudna and Emmanuel Charpentier published their discovery and invention that CRISPR and Cas9 could be used by man to edit genes in living organisms, a story captured vividly in Walter Isaacson's outstanding book, The Codebreaker. Doudna and Charpentier, as many of you I'm sure know, won the Nobel Prize for Chemistry in 2020. Now, what's striking about the CRISPR story is that it involves both a remarkable biological discovery of a defense mechanism of bacteria against viruses, but also an incredible phenomenon whereby the Cas9 enzyme can operate as a tool to cut and repair a disordered genetic sequence, a great invention. What's also remarkable is how much this discovery and invention conformed to the pattern of scientific research suggested by Bush in his Endless Frontier report. For example, 1, the innovation came from an unexpected source with no NIH or NSF funding. 2, it proceeded in a nonlinear, unpredictable manner. 3, it benefited from academic freedom and broad dissemination of information across numerous universities and research institutes across countries and continents. We could probably draw some additional parallels, but those 3 seem to be the most prominent. So what can the CRISPR story tell us about possibilities to encourage basic science and research? Well, perhaps it's time to return to the earlier point made by President Conant of Harvard and echoed by Bush. Conant says, so in the last analysis, the future of science in this country will be determined by our educational policy. So what can our educational policy teach us about the possibilities for innovative R&D funding and business models? Oops. Guess I'm going too far here. Sorry. Should be relatively easy to stay on track. Sorry. Charter schools may well be the most important educational innovation of the last 50 years. It's not a technological innovation, but rather a business model innovation enabled by novel state laws and a unique combination of features encouraging parental freedom and educational performance and accountability. What makes charter schools unique is that they have the freedom to experiment with better curricula and to hire and promote teachers based on performance, not tenure of service. Each head of a charter public school is accountable to a specific school-specific board of trustees who are accountable to a state chartering authorizer, usually every 3 to 5 years, depending on the state law. And the money follows the child and the choice of the parent of where they would like to send the child to school. With a lottery system handling situations equitably where there are more students for spots in a school. Sorry here. As of 2021 to 2022, 3.7 million students were being educated and formed by charter schools. And there were nearly 8,000 charter schools in the U.S. Charter schools educate, if you can believe it, 99% of students in New Orleans since Hurricane Katrina decimated its former traditional public schools. And 46 U.S. states have charter laws. It's become a nonpartisan model for educational opportunity, especially for the most disadvantaged families and students among us. Less well known than charter schools are school tuition organizations, or STOs, sometimes referred to as school funding organizations or scholarship tax credit programs. Pioneered by Arizona in 1998, it in part as a means to overcome Establishment Clause constitutional law scrutiny in state and federal courts, school tuition organizations are a tax-advantaged business model innovation that enables parents the freedom to send their children to high-performing independent schools. Individuals and companies receive a tax credit for donations to the STO, which in turn grants a scholarship to the student to attend an independent, private, classical, or religiously affiliated school. School tuition organizations are now available in over 20 states and funded over $2 billion in scholarships in 2023 in Arizona alone. As you can see from the chart on the right, states establish maximum tax credit levels for individuals, married couples, and company tax credits for donations. One of the more striking examples of supply-side innovation in education today resulting from STOs is the growth of classical schools. The growth of this new model of educational funding correlates closely with the increase of new classical schools serving parents and children across the country. A superficial critique of scholarship tax credits is that the schools they enable and whose growth they foster are not rigorous, and that students are likely to be performing poorly in such environments. Test scores from 2018 demonstrate otherwise. Classical high schools are outperforming other types of schools in this survey of the American Classical Christian Schools Association when compared to data taken from the College Board. So why am I bringing all these things together? Let's try to synthesize some of the insights of Vannevar Bush, the challenges facing today's federally funded scientists and researchers, the lessons of CRISPR, as well as the lessons from charter schools and scholarship tax programs to pose the following question. What new public-private business models for R&D funding are likely to promote the best of the supply side in discovery and innovation in the United States? Some reasoning by analogy suggests a couple of policy recommendations. The first is that Congress should consider using block grants, just like they did with the original Hatch Act of 1887 and the first agricultural experiment stations, to send 5 to 10% of the annual budget of the NIH and the NSF to the states. States would be free to establish their own fast-track procedures for scientists and researchers to apply for and receive such grants. This would reduce transaction costs for scientists and researchers, save them time, and increase the supply of discoveries and inventions from a broader set of smaller and regional institutions, some of which Bush noted would have latent talent and a creative atmosphere. My second policy recommendation is that governors and state legislators should pass laws to provide for the establishment of a new kind of nonprofit organization, a charter research organization, modeled on the success of public charter schools and school funding organizations pioneered in Arizona and Florida. These laws would provide tax credits for individuals, similar to the STOs that I mentioned earlier, for individuals, married couples, and institutions contributing to such basic research funding institutions. They could, of course, have caps on the amount of those tax credits as well as the total dollars that would go to those research funding organizations. The charter research organizations would be able to establish their own fast-track procedures for receiving grant requests from and making grants to researchers at schools, including universities, colleges, institutes, vocational schools, and high schools with a competency in the natural sciences, mathematics, and engineering. So I'm only going to cover a couple of these. I'm happy to share these to the extent you're interested. Obviously, there are going to be objections to these proposals. It would obviously threaten a number of sacred cows that are precious to folks. Hopefully, folks can understand the possibilities, though, of innovation. But what I'd like to do is just talk for a moment about some of the opportunities and risks that might arise from implementing these proposals. First, just a couple of opportunities that I think are worth noting. Scientists in smaller labs without the grant application infrastructure, so present in R1 research laboratories at large universities, would be able to apply and receive grants. Overlooked scientists and researchers at smaller regional colleges would gain research funding to find the next CRISPR. And I think of special importance, I think this would be useful to younger scientists who will be able to access potentially funding at an earlier age. Maybe just micro grants for small research projects, which then would get the attention potentially of the larger national funding agencies. There are, of course, some risks that come with these proposals, which I see as follows. Some funding would get diverted from our most talented scientists and researchers working at established universities and institutions, slowing their advances. Some large-scale research projects that require advanced tools and infrastructure might fail to obtain the critical mass of funding they need to continue to their next milestone. And there might also be some bioethical issues that arise where there aren't sufficient procedures in place to protect against bioethical issues or lapses, or maybe even scandals might develop. None of these risks can be completely eliminated, but prudent legislation and procedures can certainly mitigate them as we embark on these transformational new models for funding basic science and research to provide for the general welfare and our common defense well into the 21st century. I think I might have a few minutes for questions if there are any, but before I do that, I just would like to acknowledge and thank George and Nini Gilder for their multi-decade friendship, to me and my wife Mara, and to my wonderful parents, Louis and Louise Lehrman. I'd also like to thank the Discovery Institute for convening such a great group today, and especially as I think about George's contributions, Wealth and Poverty, Knowledge and Power, numerous books. I can't think of an American who's done more in the last 100 years to advance supply-side thinking and an understanding of the processes of technological innovation and wealth creation than George Gilder. I'm honored to call him a mentor and a dear friend since my college days reading Wealth and Poverty. Thank you.